All right, I think we can start. Thank you guys for coming and welcome. I always get the slot after lunch. Oh, has it been lunch yet, or are you just waiting for lunch? Great, you're still all awake. That's awesome. All right, let's see. This talk is about Kafka and streaming ETL. If that's not what you want to hear about, then you might be not be in the right room. Let's just get started. My name is Björn. I'm originally from Germany, a town called Hamburg, which is by the water, just like Chicago. I've recently moved from Germany to Canada, so I live in Ottawa now. And here's pictures of Ottawa. So that's Ottawa in the summer. And then there's a picture of Ottawa right now on the left side of the screen. It is very snowy. And then one question I get a lot is, how do you pronounce this name? And it's really, really weird, and I can't even pronounce it properly myself when I speak English, but it's pronounced Björn. When I go to Starbucks, I usually call myself Brian. It's just easier. It can be spelled like that, and that is even more confusing. And it's actually not a German name, it's a Swedish name. And there was this famous Swedish tennis player called Björn Rost. He was very famous in the 70s, 80s. And then the singer of ABBA was also named Björn. And it's a word that has a meaning, and it means bear. So that would be me. Or this one is, I guess, more proper, fat and lazy. I happen to be an Oracle ACE director and an Oracle developer champion, and just a quick into the Oracle ACE program and developer champion are programs that Oracle have put together for people that are not Oracle employees, but that do give back to the community by blogging, writing articles, presenting at conferences like this, and it's a nice recognition that they do support us in some of these travel things. So I don't work for Oracle, I work for a company called Pythian. They're headquartered in Ottawa, but we have people all over the globe. So what we do is we actually enable people to deliver work remotely, and we hire good people wherever they are, which might be in North America, it might be in South America, in Asia. I've got colleagues in India and in Europe, and it's quite fascinating. And what we do is we help clients with data problems. And we started out doing managed services for Oracle and SQL Server and other relational databases. And we have discovered that big data is big and is here to stay. So we build a big data practice. We have consulting and services around machine learning and AI. And so there's lots of things that come together. And I work in a consulting group that actually covers multiple of these technologies. And this is kind of where this talk is coming from. It's coming from me with a traditional Oracle database background, but looking to how to interface Oracle with big data solutions like Apache Kafka. And this talk, I want to start with a bit of a motivation. I want to show you a demo that I've built, and I don't know if we have the time to go into the demo by the end, but I'll just show you what this demo does, and then we get into a quick intro of Kafka, and then we go through the different steps that I built in this pipeline, in this demo that I'm showing. That's just that. So this is the big picture of what we're building. So we want to take a relational database, and we want to do some magic to it to get to a real-time analytical dashboard. And I can show you how that looks like in the end. Hopefully. Larger? Well, that's also not the right window. You need to see this window. So this is something that's already running. There's a MySQL database somewhere, and it's generating orders for wine, salt, and olives. The reason for that is I did this demo in Israel the first time, and those were products that came to mind. And we can see the sales just coming in real time and updating every 15 seconds. So the 3-4 dots that you see to the right that are not quite high yet, that's because we're still receiving orders for these time buckets. And this two-screen thing is a bit weird. And, whoa, is this big enough? I don't even know how to make this bigger. That's not how you make it bigger. Yeah, I don't know how to do this, but I mean, this is a simple command. I think we can, it's a MySQL database. Oh, I gotta look there and type here. That's gonna be weird. MySQL code. Code is the name of the database. So that's MySQL, and I need a command that I have copied here somewhere. It's just a simple insert. Oh, the monitor thing is weird. I should have practiced this. So this is the command. It's a simple insert, and I can make this bigger, by the way, I think. So it's an insert into this orders table, and I'm inserting a new product called Lumpy. We'll get to what that is in a bit. The price is 500, the user is 42, and I'm ordering this now, and just, so let me copy that into this window. this, and I'm doing another insert. Let's say this is not 500, this is just 200. And we can see this here, right? So this orange line is this new order for this lumpy product. And it's at 700 for all of these time buckets. If we do another insert now, you should see that only some of these orange things update. There we go. So basically that's what I'm showing. That's the end goal, is doing this relational database and then doing some real-time dashboard thing. It doesn't look like much magic here because it's really just a small, simple use case, and you could probably just as well query the database directly and get the numbers into some dashboarding solution. This is the whole pipeline that we're going to build. So actually I have two data sources. I have a MySQL database and I have a generated click stream or a generated stream of data. We ingest the data into Kafka using, in this case, a product called DBZM. Then we do some transformations. So these aggregations, the data that comes in is just one order at a time, and the dashboard shows you the orders per product per minute. So we do some transformations, some aggregations there. We store the data in Elastic just because the tool we use for displaying it can't query Kafka directly. And then we have the nice little dashboard. So that's the big picture, and we'll just look at the components now. Quick intro, why does Kafka matter and where does Kafka fit? Kafka fits really well into the picture of big data, and I'm not the guy who came up with this, the 3 V's of big data, but it's about volume and variety, which are two things that a lot of big data solutions cover. So Hadoop covers this very well. You can store large amounts of data, and you can use different data sources. It doesn't all have to be relational, or even doesn't even all have to have a schema. But velocity is the third aspect of big data, where you want to get insights into your data quickly, or you want to process your data quickly. And this is Kafka's definition of what they say they are. So Kafka is an open source product that they just say it's used for building real-time data pipelines and streaming apps. It scales, it's fault tolerant, it's wicked fast, and it runs in production in thousands of companies. So that doesn't really tell you what Kafka does or how it looks like. So let's see if we can get a bit of a better picture of what is Kafka. I stole this slide from the Confluent website, and this is how your enterprise might look like today without Kafka, where whenever you have to have two applications or two databases or two different sources talk to each other, we build these one-to-one connections of some sort. It could be just an extract to a file and an import, or it could be streams, it could be Golden Gate, it could be other message queues. But we build a lot of these, and we usually build them one producer, one consumer. And the promised land of not doing the spaghetti stuff is this, where you take something like Kafka, you have that as a central streaming platform where all of your events publish messages into, and then any number of subscribers or consumers can read messages from Kafka. And these can all be very different systems, right? So you see some databases in there, you see some applications talking to it directly, you see monitoring solutions consuming data, you see Hadoop being a consumer or producer. So that's really what Kafka aims to be. It aims to be that glue that holds your enterprise systems together and makes them talk to each other or easily connect with each other. To me, Kafka does 4 things. And the first thing is it's a clustered message bus. And it's certainly not the first message bus, right? So there's what's the Java thing? It's JMS, and then there's RabbitMQ, and there's tons of different message systems. So that's not something new. It's a clustered version, so they're fault tolerant. And that's one thing they do. The other thing that I think makes Kafka unique, because other typical pub/sub subscriber things don't do this, is Kafka will by default retain your data. It will store your data for however long you want to keep it on these cluster nodes and replicate it so that if one node fails, you still have access to your data. And that allows you to subscribe to topics or to messages after you've produced them. So I could just start producing whatever I want to get from my relational database into Kafka now, and I might not even know who wants to consume it. I don't have to set that up now. I can, in a week or a month from now, somebody might decide they want to look at the stream of events, and they might just consume it. Another amazing thing about Kafka is the community has done an amazing job of building connectors that are all open source to connect, or that are mostly open source, that speak to many different systems. So there's connectors for Oracle, for other relational databases, for Hadoop, for Twitter, for things like that, and you only have to configure these connectors to implement connections to new systems. And then the part that I find is really cool, and it's rather new, is actually processing these events in real time as they flow in and out of Kafka, and doing these transformations right there in Kafka. So that's the 4 things I think Kafka does, and at least the data retention and the stream processing in the same technology stack or the same cluster that handles your message distribution is pretty unique to Kafka. And I also don't know any other system that has as many connectors that are also all open or mostly open. Right, so what are use cases for Kafka or event hubs? One use case I see is linking together these systems, so just exchanging messages about a system. So you might have an old 20-year-old Oracle application that you are quite happy with, but you would like to add something like a microservice. Like every time a user signs up, add that user to the email marketing campaign and send out an email. And that would typically be a new development request, and you would ask somebody who developed this old application 20 years ago to change their monolithic code to add this connector or to add this service to it. But you don't have to do it that way. You can put these events into Kafka and just say, whatever other service wants to listen to me registering a new user, I can take action on that. Think about IoT, where you have streams of data that are so big and so fast that you can't even, or you might not be able to easily store it in a relational database. You might just want to stream it into Kafka, and then getting insights about this. So again, think about IoT, think about traffic sensors, for example. Would you really want to wait a day to analyze your traffic patterns to tell you that yesterday there was a traffic jam somewhere on the highway? No, you would probably want to get insight very quickly and see if there's, 10, 50 measurements of somebody going less than 5 miles per hour. You want to raise an alert and say, this is probably a traffic jam, we want to report this, or it might even be an accident that we haven't discovered. And then this use case today is really for real-time dashboards. So think about a real-time dashboard. In this case, it's sales data, and you want to just in real time see your sales, and maybe even enrich that with some data, which would be the ultimate goal for my demo. Getting started with Kafka. Kafka is not only used by thousands of customers, Oracle also has built a product around this. So there's an Oracle cloud service called the Oracle Event Hub Cloud Service, which you can use with either a trial or a paid Oracle account, obviously. And you can easily spin up a Kafka cluster that Oracle provisions and manages to some degree for you. So you don't have to worry about the whole setup of a cluster and all of that. There's a few slides with a lot of text, which we probably want to skip over. But I kind of want to make the distinction between state and events. So when I say streaming and Kafka, I talk about events. And an event really is just one thing that happens, and it's unbounded. We talk about unbounded data sets where just data happens to flow in. Whereas anything we do in databases really is give me the state of something. Databases are really good at storing state or at reporting the state. Give me the current money that I have in my bank account. That's a question for a relational database. But the tell me when I made a transaction, that's really more of an event. And I think that distinction is important to make. And again, the IoT thing is the same thing. You have an IoT sensor, it reports something. That is an event. The state of how many cars have gone through this highway traffic sensor thing yesterday, that's sort of a state thing. Right, so my demo uses a simple table. It's called orders. Has these 4 or 5 columns, and it's really simple. It's just a product, a price, a user ID, and then some order timestamp. And I've got a simple shell script running that just randomly inserts orders into this table. Right, so we have data in a table. We don't want to touch the database itself. We don't want to query the database necessarily directly from an analytics tool. So how do we get data from a database or from a system into Kafka? And the first place to look at would be Kafka Connect. And Kafka Connect is an open source framework that is built on top of Kafka, where Kafka itself doesn't really care about the message format. You could just make it any format you want. As long as it's serializable, you can store it in Kafka and consume it on the other end. Kafka adds support for Avro and JSON data types. If you use Avro, it has a schema registry where the producer would write the schema information in the registry, and then anybody who consumes the information would know the schema of the data that goes in. And then this Kafka Connect framework has tons of pre-written connectors. So there's an icon for Hadoop here, there's SQL databases, there's files. So it would make it very easy to just write a configuration for a connector to, for example, consume messages from Twitter and then send them out, produce messages from Twitter, write into Kafka, and then have a different connector that writes them to S3, for example. My examples use this thing. This is actually Lumpy. So when you saw Lumpy in my demo first, this is a kind of mascot of the ACE program that I used to carry around to conferences, but it's a real pain to travel with and answer questions to the TSA. So I didn't take him, and he's quite pissed about that. He's got a simple diary where he keeps his diary. So he hates the snow in Canada, and he's still jealous he didn't go to all these warm places. And so that's his diary. And if you think of this diary table, that's really easy. That translates very, very easily into events, because every new entry in the diary is an insert. It's a new insert, and the ID increases. And fetching that into Kafka is very simple with a Kafka connector that's called Kafka Connect JDBC, which will just query this table to do a select star from diary, and then it will remember the highest ID as an offset, and the next time it queries it, it will just say, give me all the IDs that have an ID higher than 18. So I do this here, I insert a new row in this table, and now it would fetch this thing. And this is all you have to write to get data from this diary table into Kafka. You write a config file where you give it a name and in this class, and then you just define the connection string. You say which table you want to fetch data for, and you say the ID column, and use that for my offset. And then it gets written to a topic. A topic is basically the table or the name of the stream in Kafka, which will be MySQL minus, and then in this case diary, because diary is the table name. And that works rather well, and this will just wake up every 5 seconds and query the database, but we're still kind of polling the database. And this is also limited if you want to look at more complicated tables like this. This is Lumpy's inventory, where he has certain things, like he's got friends and selfies and name tags, and he loves to take selfies, so the selfies row might just get updated, right? We might update that to more than this. So we update the inventory, now he's got more friends. This is something that our default config would not pick up, because the ID didn't change, and it would just say select star from inventory where ID greater than 5. It wouldn't pick up this change. So how can we make this simple connector, the simple JDBC connector, work with these updates? So one thing you could do is, if you already have this, it's awesome. If you already have something like a last modified timestamp, you could easily use that. If you don't, you probably don't want to add it to your table just for this requirement. And what I certainly don't like is this valid from, valid to, where you then have to have a lot of logic in your SQL to determine what is actually a valid row right now. One way to do it is with a method I call poor man's change data capture, where if you are an Oracle, it has a feature called flashback query, where you can specify select from a table versions between yesterday and today, and it will give you all the versions, including updates, inserts, and deletes. And Oracle does that using undo data or even flashback data archives. And I got another talk where I go more into the details of this. But just take this. This is actually the inventory table with this versions operation. So I say do select from inventory versions between min value and max value, which just means give me all the versions that you have. And then you see it actually has this. So friends started with 42, and it was an insert operation, and then friends got updated, that's the U, to 42, which was just updated on the same thing. And then there's 50 more friends, and there's more friends, it's all these updates. So we fetch all of these things that are basically events, and we can fetch this into Kafka, turn them into events, and that's a way how you can use this Kafka Connect JDBC driver, or module connector, to get changes into Kafka from Oracle. That's just a config for that. But really what you want to be using probably, if you want to get data from relational databases into Kafka, is we already have event streams in databases. Like every database that I know has some concept of read log files or bin logs or transaction logs, and they are basically streams of events. We store every insert, update, delete in some way or another in these logs. So that's there. And Oracle calls them redo, MySQL calls them bin logs, Postgres calls them write-ahead logs, and then SQL Server calls them transaction logs. And what we can do with this, and this is just one example from one product, is they take these redo logs and they mine these redo logs, write them into an intermediate format called plogs in this case. And then these plogs can be mined by a Kafka connector, stored into Kafka, and then once you have them in Kafka, you can do whatever Kafka connects to with these messages. And this is an example of DBVisit, which is a product for Oracle sources. There's a bunch of other products out there that do it for Oracle, SQL Server, Postgres, MySQL, etc. Let me skip over this. The connector that I use for this demo is a product called DBZM. And DBZM is an open source project that is sponsored by Red Hat. And they have connectors for Red Hat, Postgres, and Mongo, and they are working on a free connector for Oracle as well. They use the Kafka Connect framework, they store Avro, and it's quite simple to set up. Again, you just write a config file and you submit it. And This might be too small, but what you see here, that's the whole message that we generate. So whenever I insert into my orders table, in this case it's an order for wine for 8, whatever the currency is, that's in here. So we have this, and then we have a bunch of metadata, like the source database and the time we made this change was made, and all things that I don't really need in Kafka. So I'm looking for a way to transform this, or to just filter out only the things that I need, because what I need is only the bold stuff here. It's the ID of the order and the product and the user ID and all that. So the way to do that in Kafka Connect is to use what's called SMT, so single message transforms. And those are just simple commands that you configure in the connector config file. So when I configured this connector, I added these parameters: transform equals filter, filter type is replace field value, and then I say just whitelist everything that's in this nested type called after, or nested object. So I do this, and then the output will be just this nested piece with this thing in it. So this is awesome, and it's almost what I want. I don't need this to be nested. I kind of want this flattened, and luckily there's an SMT connector that will flatten it for me. So I add a second transform to it called flatten, and I say make the delimiter be this underscore. And now my output is this after underscore ID, after product, etc., etc. It's flat. It's all the information about this order. It's in there. That's pretty cool. I still want to get rid of the after underscore because there's no need for that. So that's a third transform. It's called rename, where I just rename everything with after underscore to nothing. So now I've got my database order. Whenever I put an order into my MySQL database, DBZM will read it. And between DBZM and Connect, it gets transformed and flattened into this. So now I have an Avro object that has all of the data from each transaction in it. So that's cool. That's the way how I get data from a database into Kafka, and nicely in Avro with the schema. So you see that the data types are correct. So that's an integer, there's a string. And then they also, and in MySQL, there's actually a date time column. Avro doesn't have date time. They only have long for this, so they store as a long data type, which is actually quite useful down the line. All right, so now I've set up my database. I have streamed data into Kafka, and now the question is, how do I process it, and what do I even want to do with this? And traditionally, when we do data processing, we talk about ETL for warehouses, where we take data from transactional systems or from several sources. We ingest them typically once, twice, 3 times a day. And we enrich them by joining tables together. We aggregate them, and we might put them into something like a star schema to make them easily queryable by analytics tools. And that's how we traditionally do with ETL, right? But the problem is it might not be fast enough. And so hot topics in analytics today are in memory, like Oracle reads their memory feature. SQL Server has this. Teradata does this, where you do stuff in memory so that you can, in theory, run OLTP and report in your same database. So that's a hot trend, really with the goal of providing something like real-time or near real-time analytics. Machine learning and AI are obviously hot, and then new data sources are coming up. So this IoT example that I talked about, or Clickstream, or other big data sources that we might want to just muddle together with our data warehouse kind of data, that's new, and I wouldn't even know how to handle some of these cases in a traditional data warehouse. Like, would I actually want to import the whole Clickstream I have on my website in an HDFS or in an object store into something like an Oracle database? Probably not. Similar with IoT, maybe we can, but do I really need to import all this data into a relational database? I don't know. So that's where stream processing, and actually the idea of processing data as it happens in a stream has started, and that's also not new. And there's a bunch of solutions that do this, with the most popular probably being Stormflink, Spark. And then the tool that I really like is Apache Beam or Google Cloud Dataflow, which allow you to do exactly the stream processing on unbounded data sets. The problem that many people have, and that I also had as an entrance barrier to this world of these tools, is that you actually have to write code for these things. So all of these tools, typically, if you want to write Java code, they all do Java. Some of them do Python, some of them do R or Scala, but really you're writing code. You're not writing just SQL anymore. So this is how I felt for a long time. I want SQL. Give me SQL, and I really want to get into stream processing. And this is here now. So this is what the core of this talk is about. It's about a tool called KSQL. And KSQL was developed as an add-on for Kafka by the company that runs Kafka. So there's a commercial offering. You don't have to buy their product. KSQL is still open source. You can use it. And the idea of KSQL is to enable you to run stream processing directly on your Kafka cluster that you already have, using SQL as the language to express your transformations, which means you don't have to write Java code, you don't have to write any other code. You just write SQL with a little bit of a syntax add-on for something you need for it. And it's an exciting time. This has been out for beta for like about half a year, and my demo is actually built on the latest beta release. But Confluent has announced that it will be GA. At one point they announced it would be GA in March 2018, which would be now. And then they said April 2018, but it's going to be any week now. So look out for this. Right now this is still beta, but it's coming into production. So what's the big deal about stream processing? Why is stream processing so different or so complicated, and why is it not the same as regular processing? And when we do regular data processing or regular ETL, we usually work on bounded data sets. The data we have in the database is usually it's bounded. We have a start, we have an end, and we know that all the data inside the database is typically consistent with respect to each other, which makes it possible to do everything we do. When we talk about streams, it's unbounded. We might not even have the data from whenever we started consuming the stream, and we certainly know that there's more messages coming in all the time. So it's kind of infinite, it's certainly unbounded, and the messages in a stream don't necessarily have to be consistent with respect to each other. Also, you don't really get a guarantee for timeliness of messages. It might just be that your messages come in late either because the system that produces the messages are just late in sending them, or because of some networking problems. It might be that you receive events out of order, so you also have to take care of that. And the kind of transforms you want to do, to me there's three kinds of transforms. The first one is easy, and I've already showed it, is the single element transform. If you just need to take a single element and change its shape, like you need to flatten it, or you need to filter out certain columns, or you need to apply a function to one column or to one data element, that's kind of easy because you don't have to look at other elements in the stream. And you can do that with the single message transform that I just showed. And KSQL can do it too, and Kafka streams can do it. There's many solutions that do this. This is simple, this is easy. And again, that's just my examples of that I showed earlier. The harder solution is, how do I do aggregates in an unbounded data set? Like, how do I count all of the orders for salt or for wine or for anything like that? That is obviously easy on a bounded data set. We just do a group by in a database in SQL. That's easy. But how do we do this on an unbounded data set? What does it even mean if I say select the sum of all orders group by product? What does it even mean? And how do we do this? Because it's unbounded. We don't have a start. We might not have an end. And the solution to this is this. It's windows. Not the windows that this logo is for, but it's these kinds of windows. So you take your unbounded stream, your having no end, no beginning kind of stream, and you break the stream down in windows. And this is an example of what's called, these are tumbling windows. They don't overlap, they have a fixed size. So in this case, each window is 5 minutes in size, and now we can take all of our stream events and put them in one of the windows, and we can easily group, aggregate, and do stuff on each window. This sounds way too simple. It's not quite as simple as that, because what might happen, as I said, there's no guarantee for events arriving in order and for you processing events at the time when they actually happen, so there might be a bit of a delay. So take this example where at 8:17 there's a new event. That shouldn't be cut off, by the way. There's a new event that has a timestamp of 8:02. So what do we do with this? Does this event go into this bucket because that's when we process it, or should it go in this bucket? And logic says if it's the event timestamp and we window by the event timestamp, because that's usually what we want to do, we want the sales for the window of 8 a.m. to 8:05, then we need to make sure that we put this data piece into this bucket. And KSQL and any other streaming solution would actually do this. But then the question also arises, how long do we do this for? Like, how long do we keep this window open for? Do we keep this open forever, or for an hour, or for a day? And what do we do with late arriving data that comes after that? That's an example of, I said, tumbling windows. So they're fixed size, they don't have any gaps. It's probably the easiest window type to understand. The second type of window that streaming solutions typically support is called a hopping window, where the length of each window is fixed. In this case, it's fixed to 5 minutes, but we open a new window every minute. And I'm actually using this in my demo. If you remember back the demo, it had 4 or 5 data points that were still kind of growing in size. And that's because I had actually 4 windows that were open for a minute each, but it started every 15 seconds. And it's just so that the graph is a bit more dynamic. And then I got lazy with the slide and it didn't copy and paste all the pieces together. And the third type of windows is called a session window, where the size is variable in size. So you might say, I want to create a window every time a yellow event happens, and I want to keep this window open until no event has been happening for 3, 4, 5 minutes. And this is obviously useful if you want to do clickstream analysis and you have a web session and you want to say, I want to keep these events together in one window, as long as there's some concept of a session still being active. Right, so now that we know what a window is, it's really easy to write SQL. So this is actually a KSQL statement where we create a table on an order stream. So we have a stream called orders, and we create a table on this as select the product, the sum of the amount that we ordered from this stream orders. That's a stream, that's an unbounded data set. And we create it as a window hopping, 60 seconds each. It advances every 15 seconds, so for every minute there will be 4 open windows or 4 active windows, and we do a group by product. And then I do this little thing where I just enhance it with the timestamp associated with each of them, and that'll just be useful for displaying them in actual window buckets. And if we have time, we can go into the demo and actually look at these streams. This is the stream for this. So this is I just created the orders per minute or the orders per minute timestamp. Suggesting a Microsoft update. And we can see this is the window start time, and then this is the product, so we can see that there's these 4 active windows for olives, and we can see that this is the amount. So this is probably the newest window that's only been open for the last 15 seconds, so there's less order amount in there, and then as we keep going with the demo, it'll just increase these numbers. So we get, for each window, we actually get more than 1 update. Like every time you have a new event, it will actually update all these 4 windows for us. This is just something I copied. These are the functions that you have available now. So it's, and you notice that it doesn't have an average. So there's no streaming function for average, which is kind of hard because to have the average, you have to have all the previous data. If you want to build something like an average, you have to do it yourself, and you have to count them and then divide by the, sum them up and divide by the count to build your own average. So that's how you do aggregates in streaming. And this is already pretty powerful, and this is something that you couldn't do otherwise. Right? Of course, you could run queries like this directly against a source database, but doing them in stream processing piece by piece, you just can't. And the last challenge really is what happens if you need to join together 2 data sets or 2 data streams. And I'm doing this in this demo too, where I take, I've got a separate stream called users, and the users have levels, so they're either gold, silver, or platinum. And my orders only have a user ID. So what if I want to group by the order amount by user level? For that, I would have to join together the user information, like give me the level for a user per user ID, and join that together with the orders table where I only have the user ID. And that's something you can also do simply in KSQL. It's just a simple join command, just like any other, pretty much like any other join you run. KSQL right now is limited to joining tables to streams. And a table in KSQL has to have the concept of key, so you have to define a key, and each key can only have 1 element. So it's a bit different from a stream where you are free to just stream anything. I hope they will lift this eventually. This is how the syntax would look like. So I'm creating a table inside of KSQL called users from a Kafka topic called localhost code users. Type is Avro, which means I don't even have to specify which columns this table has because it'll fetch this from this Avro schema. And then this is my join. So I create a stream called orders_users as select order stuff and user city and user level from orders, and I left join the web users, it should be called web users up here, on the user ID. So I do that, and I get my, I can query this, and I can get my order volume per user level. Right, and at this time, I'm pretty much done with the talk, and I've got a few more slides that I would probably go through, and then if you have any questions, feel free to ask questions. Otherwise, I will probably just dive into the demo and just show you some of the commands as they are. Yes?
So when you have a create table statement, what is that creating as a table, or is that something other than the table?
Okay, so yeah, the question is, when I do a create table like this in KSQL, what does it create? And what's the other thing that you can create? So you can create two different kinds of objects in KSQL. They're either tables or streams. The difference is that you can query a table and it will return only the latest event per key. So think of the users. The user has a user ID, and if I just stream data in there, I will have, initially I will just have one stream, and if I do a select star from this table, I will get what I just put in there. But now assume I modify user, so I have a new event for the same user key, the same user ID. If I select from the table, I would only get the representation of that last state. I will not get two rows back for these two events, the create and the update. I will only get the last row back. And the reason for that is, or why this is important, is because Kafka is immutable. You can never update data in Kafka. You can only truncate data that's old, or you can add new data. How is this persisted? Both streams and tables in KSQL are persisted as topics again. So as you do your transforms, they will actually all become topics in Kafka, which is both good and bad. The good thing is that you can actually use these topics and subscribe to them and look at them. The bad thing is if you do a multiple step transform, you get multiple topics, which could mean that for complicated pipelines, you have one order coming in, and then this one order has 3 or 4 or 5 transforms on top of it, and then it might produce 3 or 4 different topics, which will just easily inflate the amount of data you have to process in Kafka. Good question. Yes?
What changes do we need to make in the database study on
what changes do we need to make in the database? So that depends on how you fetch the data from the database. The first method I showed was using polling, where I used the Kafka Connect JDBC driver to pull data, basically to just always query the database and say, give me the new data. So for that one, you wouldn't have to make any changes. As long as you have an ID column, a primary key kind of thing, you're fine. If you do the log-based mining, you have to make sure that your logs contain all the information. And in MySQL, you have to make a small change, which is, I can't remember what it is. In Oracle, you have to enable what's called supplemental logging. It just means that they have to add a little bit more information to the redo stream for the redo stream to be parsable and to make sense. Other than that, you don't really have to make changes, which is also why I think that Kafka is a really, really cool tool. Because like I said, I've got many clients that have these old systems that they don't want to touch. They don't want to make code changes. Maybe they can't make code changes because it's a third-party application. They do not really want to modify the database. So in this case, you can either pull the data, no changes made or necessary, or as long as you have force logging and supplemental logging enabled, in this case in your Oracle database, you can mine the redo stream and you can just put it there. And you don't even have to process stuff inside the database. So that's the other really cool thing, where you can just attach things or do analytics on your database without having to query it. Right, so if you're interested in stream processing, there's other things. So I really like Apache Beam and Dataflow a lot, and they've got some more constructs where they have a lot more in terms of how do you handle late arriving data, when do you close a window, how long do you keep a window open. And they have something that KSQL doesn't have, which is triggering events. What I said earlier is that every time a new event comes in, it will update this window every time, which means that if I have 1,000 events per second, it also means I update my window 1,000 times per second and write that to, in this case, Elasticsearch. And in Apache Beam, you can say only do this once per minute and only write it out persisted to disk or to whatever you write it to. And then for late arriving data, only do it whenever it arrives. So there's that. What do I like about Kafka and KSQL? It combines storage and processing in one platform, so you only have to have your one Kafka cluster, and it's highly likely to use Kafka anyway if you need to ingest streaming data sources. It has this support for so many connectors. Like I also love to work with Google PubSub, for example, but they have a very limited amount of connectors, and every time you want to put data into it, you have to write custom code. And then if you want to get started with stream processing and see what's possible and see what you can do, KSQL is the simplest thing you can use to explore. Especially if you're coming from the DBA world, you probably already, if you're coming from the DBA world, you should already know SQL. And writing KSQL, if you know SQL, is really simple. Whereas writing Spark or Dataflow or Apache Beam code, if you're a DBA and you are not that great with Java, it's a bit of a task. The cons are, A, it's not really released yet. It's still beta, and there are some kinks in it. The joins are somewhat limited to simple things like what do you do when you want to join a large table? What do you do if you need to enrich your data? Like this user example. It's simple if you have 100 or 1,000 users, but what if you have 5 million users? You can probably not hold 5 million users in memory, but you kind of need it in memory because you need to look this up for every event that comes in. And then it has some limited math for ETL, so there's no case, no NVL, no other things. You can always use Kafka streams, which again is Java, Scala, R code to enhance it. And if you're running stuff on the cloud, you still run VMs if you run Kafka most of the time today. There's a bunch of links. I'll upload the slides later, or I'll give the slides to the organizers so you can get them. There's some links to get you started, especially with the KSQL and getting data from relational databases into Kafka. And I think this is my summary, which is databases can talk streams. So if your company is talking about streams and putting together a streaming data hub, then you can put your hand up if you're a DBA and say, yep, I kind of have an idea of how we can do databases to streaming. Stream processing is, I would say it's still very young and not too many people are doing it, but I see a lot more requests for it every week. Customers are asking, I want to get analytics faster, I want to get intraday numbers for sales and for other things. IoT, you don't want to wait a day to process your data, you want to have insight into it very, very quickly. And I'm really excited about KSQL because it's just so simple and cool. And I would have 3 more minutes. I could fuddle around and try to get the demo, but I think that's more valuable to answer questions.
Could you go back to the previous slides?
Oh, sure. Any other questions? Yeah.
Did you say in the code that you might have multiple clusters of Kafka?
I had a hard time hearing the question. Can you speak up?
The question was, if I want to have multiple clusters of Kafka, when I'm transferring from RDBMS to
Yeah.
ready to perform or
I missed the last part. When you have multiple, you said when you have multiple clusters of Kafka, how do you handle that? Well, so the first thing is, what I said is when you do the transforms, you get multiple topics. So a topic is just basically an organizational structure to put messages together. So that's just topics. You can also set up multiple clusters. So you can also create multiple Kafka clusters, and then the clusters can talk to each other with a tool called Mirror Maker, which is basically one of these Kafka connectors where you specify here's my source Kafka cluster, there's my target Kafka cluster, and now please replicate the messages across. Does that answer the question? Cool, or just find me afterwards. I just had a hard time hearing you. Yeah?
What would be the purpose in general of Kafka clusters?
What's...
Are they multiple instances? Are they multiple machines? Like a cluster? I'm not sure I understand the concept.
Yeah, fair enough. So the question is, what are the purposes of these clusters? Why is Kafka a cluster? And I think that's for 2 reasons. It's for high availability and for scalability. So one thing is you want to have multiple nodes that if one node fails, you can still consume and replicate messages. The other reason is it has its own local data store. So Kafka will store and persist its messages locally on the cluster nodes. So if you want more storage, what you'll have to do is you'll have to add more nodes to your Kafka cluster just to get more local storage. Just like, I would say in the early days of Hadoop, where you had to store everything on HDFS. And in order to grow HDFS, you had to add nodes to your cluster. So that's the purpose of why Kafka runs in a cluster. My demo obviously just runs in a single Docker image, and it's just one single thing. But you build these clusters mostly for HA and scalability. And then also, that's the other neat thing, is when Kafka was first released, it was really just a message hub and a distribution center. And you would really only use it for that. But all the code that you run also runs inside of a Kafka cluster. So the simple case, my JDBC connector, the thing that connects to a database and reads and pulls data, that will also run in my Kafka cluster. And they will make sure that to run this, this connector on one or more nodes is needed, and also relocate it if a node goes down. And then as soon as you get into the KSQL, you actually, what it does underneath it will actually create Kafka stream jobs. And these jobs also have to run somewhere, and they also run on the same Kafka cluster, which is, I think, kind of nice because you combine the storage and the message distribution with the processing. Whereas if you use something like Spark or Dataflow, these are two separate things. You have a message distributor, which could be Kafka, like Spark, and would work with Kafka. You would read messages from Kafka, but then you have to have your Kafka cluster for storing messages and distributing them, and you have your Spark cluster for processing messages. All right, I think, yeah, one more.
In an enterprise, you care about all the message sequencing, right? It's not like you can update the way it comes in the message reaches your destination. How do you do all message sequencing? Do you have a vision to take care of that?
How do you measure message sequencing?
Sequencing, right? So for example, if you are talking about
Carrying what?
right, I need to apply the changes in the right sequence, right?
Yeah.
By destination, right?
Yeah.
I cannot go like half of our way, right? Do you have that kind of message sequencing capabilities available here?
Yeah. So the question is, how do you deal with message being out of sync and replicating this? So one thing is, Kafka is probably not the best tool if replication and replicating state to state is your goal. Like if you want to take an Oracle database and replicate that to a SQL Server database, there's probably other tools that do this better than Kafka. That's probably the answer to that. And then if you do your aggregations, they take care of aggregating it to the right place. If you just add the transactions and what you keep on the other end is just it's not a table that has state, but it's just a table that has each event in it, then you also don't worry really much about that. So one way you could do is that you could take your source system, store event for event and row by row in a destination table, which would then kind of make it a bounded data set. And then once a day, for example, you could say, well, now I'm pretty sure that all my events have arrived, and then you can do whatever you need to do with it to do it in order. I think there was one more question, and then I think I get to get kicked out of here.
Thanks, Sam. If you need more sophisticated reordering and window handling, you send Kafka and then
Or that, yeah. Fantastic. I hope this was useful. I really appreciate all you guys coming out. I think now is lunch. Thank you.